Chemistry Higher Paper 2024, question 10. Okay, we've nearly got to the end of the paper. Well done for staying with me. Okay, so it's a dynamic equilibrium question to finish off, and there's loads of information given to us in this little blurb at the top. So we've got our balanced equation. We're told there's a nickel catalyst, and we're also told that the forward reaction is endothermic, which comes up very relevant a little bit later on. Okay, so describe the effect of the catalyst on the rate of attainment of equilibrium and on the equilibrium yield of the products. So we've got two things happening in this question. We've got two topics that we're having a look at in one question. One question is about rate, and one question is about the equilibrium yield. So remember that a catalyst will speed up the rate of a reaction, so therefore the rate is increased. I remember that a catalyst increases the rate of the forward and backward reactions at the same time, so it will reach equilibrium more quickly. And then secondly, catalysts have no effect on equilibrium yield. They just make both forward and backward reactions quicker. And then we have this 6-mark question that I know lots of people found quite nasty. But if you break it down into its smaller parts, it's not so horrible. So we're told we've got a temperature of 600 degrees and a pressure of 20 atmospheres. We have to say what would happen to the rate and to the equilibrium yield if the manufacturer was to use a higher temperature and a lower pressure and the same catalyst. Now remember I said we're coming back to the fact that it's an endothermic reaction, which is super relevant for answering this 6-mark question. So what I would do here is I would have a look at the difference or the impact of both of these. So I'm going to start with increased temperature. So let's have a look at rate first of all then. So faster rate of reaction, so equilibrium is attained more quickly. That's my starting point. Let's say Y. Remember, we know from our rates topic, higher temperature means more frequent collisions. So that's why the rate's going to be increasing. And remember, you're going to have more particles with a higher energy as well. If we talk about the yield, we know from talking about Le Chatelier that when you make a change to the equilibrium system, it will alter itself to compensate for the change. So if we're increasing the temperature, it's going to move more to the side that will cool it down. And remember, we said that the forward reaction is endothermic, so it's absorbing the heat energy in the forward reaction. So therefore, higher temperature favours the forward reaction, as the forward reaction is endothermic. So higher temperature, you're going to get a faster rate of reaction, so therefore attain equilibrium more quickly, and you're going to favour the forward reaction because it favours the endothermic reaction in this case. Then we talk about decreased pressure. So, again, talking about rate, the rate decreases because there'll be a lower frequency of collisions. Okay, so there's less that's pushing those particles together. Then our yield, let's just go back to our starting equation. Remember that we're looking at the number of gas particles on each side of the equation. So on the left, we've got 1 methane and 2 water. So that's a total of 3 molecules. On the right-hand side, we've got 4 hydrogens and 1 carbon, so a total of 5 molecules. So if we decrease the pressure, we're going to favour the side with more gas particles, which is the right-hand side, and so therefore the yield is increased. So decreasing pressure favours side with more gas particles. So yield is increased. And that's all you would need to get your 6 marks. Okay, the rest of question 10 then. We've got a nice bit of calculation to finish off with. We've got, again, our reaction taking place here. We have to calculate the maximum volume of products in decimeters cubed that could be formed by the complete reaction of 650 decimeters cubed of methane. Okay, so what this is telling us is that 1 mole of gas in this situation has got a volume of 650 decimeters cubed. And remember that in gas reactions, a mole of gas, no matter what the gas is, will have the same volume as a mole of any other of that gas. So we are having a look at our products here. We've got 5 moles of products. So therefore, all we need to do is multiply 650 by 5 to get us 3,250 decimeters cubed for our answer there. And then the final part then, we have the same reaction. We're calculating the maximum mass in grams of the carbon dioxide for every 1,800 decimeters cubed of hydrogen. Okay, measure the room temperature and pressure, and we've been given the formula mass of carbon dioxide, and also this handy tip here that a mole of gas at room temperature and pressure is 24 decimeters cubed. So the first thing I'm going to do, I've got 1,800 decimeters cubed of hydrogen gas. I'm going to find out how many moles I've got. We know that 1 mole is 24 decimeters cubed. So 1,800 divided by 24 will tell us how many moles of gas we've got. And that gives us 75 moles. Then we need to know how much carbon dioxide we've got. Now we can see here it's a 4-to-1 ratio in the reaction. So to find our number of moles of carbon dioxide, it's going to be 75 over 4, which gives us 18.75 moles of CO2. Then we need to use our moles equation. We know that mass equals Mr. moles. Our MR is given to us up here. It's 44. 44 times 18.75 gives us an answer of 825 grams of carbon dioxide.